Okay. Yeah, he has to miss part of the class, and I would like to have a sample of this anyway. All right, so whenever you're ready, you can unlock the door to the waiting room.
Sure. Give me 2 seconds. Ed, you're muted, so whenever you're ready, you're gonna have to unmute again.
Okay, welcome. Are people in out of the waiting room?
They're still slowly joining, but I'll add them in.
All right, I think I need to start though, because we have a lot to cover today. So, greetings, everybody. This is the second lecture in the class you signed up for related to the foundations of quantum mechanics. And let me just reduce some. So you're looking at the Word document that I use to build the various chapters. It's you'll see why I'm doing it this way in a second. Interesting here, this picture, this cover picture. I'm going to zoom in on it. This is a house in Leiden in the Netherlands. And if you look closely up in the upper floors here, I'll tell you what that means. This house is the building in which Uhlenbeck, mentioned here, and Gaudsmit first conjured up the idea of spin, S-P-I-N, spin of subatomic particle, or yeah, subatomic particles and atoms themselves. And it's now, I think, a private residence, but at the time it was part of the university. We will talk about this concept of spin quite a bit. Now you're watching me learn how to do this gracefully. So, last week we covered the key points related to quantum mechanics. Then remember, there's a table in chapter 1 that lists the non-intuitive aspects, which is roughly a dozen items. The way that quantum mechanics behaves that's so unlike the way the classical physics of Newton and his intellectual descendants describe the world. Remember, they were working on a variety of things, including gravity, electromagnetism, the behavior of gases and solids from a thermal point of view, how they store heat and so forth. The classical physics also was very focused on observing the spectrum of various chemical elements, including those in stars and the atmospheres of nearby planets. So there's a whole classical world of physics that was evolving slowly, making observations, but could not explain what they were seeing, in the sense that they saw a color spectrum from, say, helium, but they had no idea why that spectrum was the one associated with helium. In 1900, we made the first step toward understanding those sorts of things when Max Planck discovered the quantization of light coming from hot surfaces, and eventually people learned that everything produces black body radiation. That's the topic Planck worked on. And if you've ever seen an infrared camera picture of yourself in a museum, you can see the glow of your skin It's invisible and it's called infrared radiation. So we're going to get into all those topics. And just as we did last week, I have highlighted with these purple boundaries things that I want to emphasize in what I'm going to say to you. You can read the rest of it. I hope it's readable. So let's talk about the key discoveries that were provided information so that when the new idea of quantum derived from Max Planck's work, when that became a thing in the physics community, it either produced new ideas, as we will see, or it began to clear up understandings that people had not had about why things behaved the way they did. For example, prior to 1900, chemistry was maturing science. Chemists knew about how various kinds of elements, when mixed together, produced compounds, molecules, and so forth. The concept of atoms was not mature, but the idea that from chemistry was that you could form molecules that performed different kinds of functions or represented things we saw out in the universe. And furthermore, as soon as the idea of quantum came forward, new focus was placed on the structure of these atoms that, once again, were still, their existence was still in doubt, but a transition was being made by chemists and physicists into understanding the structure of atoms. So we're going to go through that in a second. And that led to the discovery of new particles. And they got named according to the Greek alphabet, alpha, beta, and gamma. We're going to go into that in some detail. In addition, people were working to understand and characterize spectra from elements exposed to different techniques of excitation. So if you take helium or hydrogen and put it in a container and run an electric current through it, you can generate the atoms take on higher energy levels and reveal their spectrum. But additional interesting details came out of what happens if you do that experiment in the presence of an electric or magnetic field, because then you see something really interesting happen. We'll talk about that. Here's the black body equation that Planck discovered. Einstein struggled to convince his community that light is carried by particles. As I mentioned the last time we were together, Newton had this idea hundreds of years earlier than Einstein and Planck. And his idea of corpuscles, that is, little chunks of energy conveying light, that stood among the scientific community for hundreds of years until the double slit experiment that I described briefly last time. And we're going to see the double slit experiment over and over. The double slit experiment very distinctly shows that light is waves. It also, because of Einstein's work, eventually we discover that light can take on wave-like or particle-like behavior depending on how you design your experiment. And Einstein was directly involved in convincing the community that photons were a real thing. And it took a long time to do that, even after he had demonstrated understanding of certain kinds of experiments that could not be explained another way. Today, we're going to talk about Niels Bohr's planetary model of hydrogen and other simple atoms. Turns out his theory was wrong, but it was a fantastic first step. And that happened in 1913. Eventually, we get the uncertainty principle from Heisenberg, more to come on that, and a related issue related to Einstein's work is this so-called wave-particle duality. Experiments were done in the early days of quantum mechanics that showed this kind of behavior, that quantum objects can take on wave or particle characteristics depending on how you experiment on them. And I want to point something out that's always going to be in the back of my mind, and I hope yours too. Experiments in quantum physics happening in laboratories reveal details about how quanta work. But quantum mechanics is occurring in nature all the time. The process by which the sun produces light and thermal radiation and so forth, those are quantum mechanical processes. And of course, we can design experiments in the laboratory where we exclude distracting effects so that we can study the simplest possible version of something like looking at the spectrum of a gas. Nonetheless, quantum mechanics is going on all over the universe all the time. And so we will see as we go through this class that knowledge of or observation of astronomical objects reveals information about quantum mechanics as well. Here's the reference to the spin issue in quantum mechanics, rediscovered or proposed by Uhlenbeck and Gauss-Schmidt when they were both young graduate students. We're lots more to come on that topic. And in addition, we have another property of atoms, that the motion of electrons around the nucleus also produce a similar effect. See, this is called spin angular momentum, and then there's a version called orbital angular momentum, and we will get into that as well. So we have multiple experiments described in this chapter that were key to educating the community in the early 1900s who had grown up with classical physics. Everybody who was prominent in the early days of quantum mechanics was trained in the classical physics of Newton and Maxwell and others, because quantum mechanics didn't start until 1900. So the first generation of key individuals had to train themselves to set aside the biases that they had taken on because their training was focused on classical physics. It wasn't until the 1920s that the first generation of young scientists who weren't infected by the old physics, and they did not have the same barrier to create new ideas and ignore some of the biases that the older generations had about what's going on in the world of physics. So in the early 20th century, a struggle was underway, for example, in chemistry, to explain the periodic table of the elements. You've all seen this before. This version of the periodic table comes from an article in Wikipedia on where the elements in the universe come from. And so this key is present to tell us that hydrogen, and almost all of helium and a little bit of lithium all were created in the Big Bang at the beginning of our universe, our observable universe. And the color code tells us how the rest of the periodic table emerged. You'll see the gray areas here, roughly half the nickel, more than half the nickel in the universe comes from exploding white dwarf stars and so forth. But to build this modern version of the periodic table, you have to understand how atoms are assembled. And we're going to cover that in this class. And there's more history here that I'll let you read. I've already mentioned that chemistry or chemists had been making considerable progress in understanding individual atomic elements. And by 1860, a version of the periodic table existed, but explaining why it was could be organized in the way it was, that had to wait until the 1920s and the use of quantum mechanics. Here you see a history of scientists thinking about molecules and atoms, trying to understand the size, the mass, the method that goes on when you assemble molecules. And nowadays we have a topic called quantum chemistry. The former Chancellor of Germany, Angela Merkel, has a PhD in quantum chemistry. This is a branch of science that's has one foot in chemistry and one foot in physics. So as we continue to scan over the history, we see that Einstein, who the shadow he cast was enormous all the way until his death in the mid-1950s, he found three independent ways to calculate Avogadro's number. You remember that's a thing you learn in chemistry about the relationship of the mass of a particular element and how many atoms are in that mass. And so there was progress being made. A lot of the progress came from experiments mostly in the 1880s and 1890s, when scientists were able to build these kinds of glass enclosures and isolate some kind of a gas to put in there and then run an electric current through there. And in the process, the electric field ionizes the gas. And so you see a light coming from the gas, and you can study the spectrum. Here's a little more detail in one of these things where we have included not only that there's a glow that comes from these so-called cathode ray tubes, but in addition, if you have a skilled glass blower working with you, you can put metal plates here and add another voltage across there, and then you can steer the beam. And when that was observed, people realized these particles being created by the voltage between in the display in the tube, that you could steer the beam with positive and negative plates. There must be charged particles traveling in the tube. And of course, this is a first step in the development of the old style of television tubes or television displays. Now, I mentioned that new particles were found. And let's take a look at some of the observations that people made about what's coming out of either natural or artificial radioactivity. From natural radioactivity, such as radium studied by Madame Curie, people realized that something was coming out. They were called alpha particles. It turns out these are in fact particles. They are the nucleus of helium, 2 protons, 2 neutrons together, and that this, for some reason not understood initially, the alpha particles would not pass through a sheet of paper. And how would we know this? Well, we take a sheet of paper and put a film behind it. And in fact, a lot was learned by accident. When photography was becoming mature, manufacturers of photographic films would pack the sheets of film in black paper envelopes. And there are stories about how just leaving these things around the envelopes around in an environment where there was radioactive material, and then go use that film for some experiment and discover the film was already exposed. And it had been exposed by radioactive particles, initially called still called alpha particles, that penetrated the paper and exposed the film. Henri Becquerel is famous, French scientist, famous for being one of the first to just try to figure out, why is my film being damaged? Most people would just throw the envelope away and assume the manufacturer sold him a bad product. Becquerel actually exploited this observation to do science. Then we have beta particles. It turns out beta particles are electrons. They can be thrown out of a nucleus of a radioactive material, and they are not impeded by paper very much. They pass right through, and even it takes some thickness of lead foil to stop those particles. They're more energetic. And then we have gamma rays. Now, gamma rays are not particles. At first, this was not understood, but gamma rays are photons. They're little puffs of light, highly energetic puffs of light, and they go sailing through paper and lead, and you need some substantial amount of lead to stop them, 10 centimeters of lead. And I'll just mention real quickly, today we understand the whole family of subatomic particles. Included in that family are neutrinos. You might have heard of these. These are kind of ghostly particles. They're very hard to detect. And if we had a neutrino on this chart, it would pass through paper with absolutely no trouble. It would pass through this film of lead, this foil, no trouble. No trouble with 10 centimeters of lead. In fact, the average neutrino passes through 100 light years of lead before it interacts with the lead. We'll talk about that more later. Now we can talk about the first efforts to discover the structure of atoms. The successful ones were done by Ernest Rutherford and his students. I'll show you their experiment in a second. They used radioactive sources to illuminate gold foil. And their intent was to determine how much of the radiation from the radium got absorbed in the foil. And they discovered some very interesting things. And here's a picture of their experiment. So here's the radioactive material in a lead container and a couple of slits just to collimate this beam, because without that, you would have radioactive particles flying all over the laboratory. But they put these slits here. I think it's hard to see, but one's horizontal, one's vertical, and you get a nice collimated beam from that. And you can steer the beam around because with these plates hooked to a battery, you can study the electrical properties of the particles coming out of the radioactive material, and you discover the gamma rays don't get deflected by these electrical plates. No matter what voltage you apply, the gamma rays fly through. Oh, by the way, this piece of a cylinder has a photographic emulsion on it. That's how they figured out what was going where. And the gamma rays expose the film, and they are not deflected. That was an important early observation. We now know why, because gamma rays are photons. They don't have a charge. Beta particles got deflected by these plates because they're negatively charged electrons. And the alpha particles are positively charged, and they got deflected the opposite direction. So this is the first step in understanding what are the properties of what comes out of radioactive materials. Now, I have to remind you about the timing of this. This is like 1908. Marie Curie and her husband were busy studying the properties of radium and investing their lives, in fact, giving their lives, in the case of Madame Curie, to understanding radioactivity. She eventually died of various types of cancer associated with her exposure. Here's Becquerel. I mentioned him accidentally finding that uranium exposed photographic material, even though it was black or wrapped in black paper. And the black paper was used because it's sufficiently dense to prevent just regular light, sunlight and artificial light will not go through enough to expose these photographic plates. And it says plate here because early photography, the photographic emulsions were put on glass plates. So Rutherford continued his work. They were able to, the community was studying these various particles that are coming from radium and were able to get the mass to charge ratio of electrons, not individually the mass or the charge, but this ratio. And that's an experiment that undergraduate physicists at universities do to this day, is measure the ratio of mass to charge with simple experiments. Here's an example of a chemical molecule of radium bromide glowing in the dark in the Curie's laboratory. In fact, there were parlor games that people were involved in where they would buy little samples of various kinds of radium oxides and so forth, and turn out the lights at their home, close the curtains, and you could see each other glowing, or you could see the glowing material. So there's a little historical photo of Einstein and Niels Bohr. What we're going to is this. So if we take a discharge tube or a source of light, and we have a slit to collimate, again, we want to collimate that beam and shine it on a grating that is a piece of metal etched with tiny little grooves, thousands of little grooves per inch, or other kinds of methods of making gratings, then you get this from the discharge tube. You get all these spectral lines. Now, I'll remind you, the human spectrum is kind of good from here, blue, through green, yellow, and red. This, and we start losing the human eye loses its sensitivity to violet and ultraviolet light, which if we had the whole spectrum here, the ultraviolet area would be here. Humans also cannot see infrared, which would be over here. So there was a lot of characterization of the spectra of various gases that were isolated by using chemical techniques and trapped in those glass tubes I show, the cathode ray tubes. We now know that this is what's going on. This is the spectrum of hydrogen, and it includes some highly energetic transitions in the blue, or the ultraviolet, where you, by putting the electric current through this tube of hydrogen, you give the hydrogen atom, elevate its electrons to higher energy levels, and then when the electron is in the higher energy level, it can fall to what's called the ground state, and the length of this indicates the amount of energy that's released in that case. It's also true if you hit the hydrogen too hard, if you use too much voltage in your discharge tube, you ionize the atom, and the electron is separated from its nuclear partner, the proton, and that will produce a transition, but essentially you turn the hydrogen in that case into a plasma. Then we have the Balmer series, where you're more careful about how much energy or how much voltage you use. These are visible transitions, and the Paschen series are transitions allowed in hydrogen, but that produces infrared. So here's examples of different kinds of discharge tubes. And because I'm right here, I'll make a little edit there. Now, I mentioned earlier that if you have in your discharge tube, you have plates, electrical plates. You can use those to create what's called the Stark effect. So imagine that you don't put any voltage on those plates. You just run a current through through the hydrogen. And I want to point out that there's some numbers here. And see those N numbers that range from 2 to infinity if you ionize the gas. So let's look at a case where we've energized the electrons to levels, energy levels 15 and 16 and so forth. You will get these colors come out. But now let's turn on the electric field that you build in using those plates in the discharge tube and impose larger or smaller amounts of electric field. And you see the colors shifting. Not only do they shift, they split. So this particular spot right here might have been, let's say, a green emission from the hydrogen with no electric field. Now we turn on the electric field and gradually increase it. Not only does that line continues to exist, it gets altered somewhat, but suddenly we have all these different lines. In this case, it's the same kind of thing going on. The higher the electric field, the more lines you see, and they spread out. This is called the Stark effect, and it was initially poorly understood. At the same time, Zeeman was doing experiments. I'll show you the Zeeman effect here in a second. Here it is. The same thing happens. Here are transitions in hydrogen, but in this case, we're not going to apply an electric field. We're going to apply a magnetic field. Oh, and these are rubidium. So this is the result of modern experiments with rubidium. With no magnetic field, you get emissions related to these 2 points here. If you turn on the magnetic field, you get splitting. This was not understood. But the seed was planted because once these results were created in the late 1890s, people were always thinking about where does the Zeeman effect come from? Where does the Stark effect come from? What's going on here? Now, I've mentioned a couple of times infrared. Here's a drawing depicting William Herschel, the discoverer of infrared radiation, and how he found the existence of, and this is in the late 1700s. He lets the sun shine on a prism, and on the table in his office, you could see different colors visible to humans. But he also had this rig he set up with thermometers. And he placed those beyond the visible sensitivity of the human eye. And as soon as he uncovered the cover that was on this prism, he sees the temperature in these thermometers going up. So he knew there was something out here that he could not see, but it was warming the thermometers. And this is the first evidence of infrared radiation. As in all through the book, you have these hot links you can go to get history and a biography of Herschel. He was just a powerful thinker and produced a huge telescope and so forth. So he's an interesting person to read about. So we have these effects, the Stark effect and the Zeeman effect, indicating that atomic material is sensitive to electric fields and magnetic fields. These depictions here are the modern explanation for these splittings, where this transition in rubidium from an energized state to the ground state, the splitting is the result of imposing a magnetic field. And today we explain this as having to do with the spin of the electrons in rubidium. And we'll be talking about that a great deal more. So let's talk a bit about Let me reduce this a little bit so I can see 2 pages. We're going to talk about Planck's discovery because it was so critical to the emergence of quantum mechanics. His discovery occurred convenient and easy to remember in the last month of 1899, and his paper and presentations to the science community came out in the early in January 1900. So we have these curves, these so-called black body curves that had been measured usually in industrial settings, and most of the effort to measure these curves had to do with making factories more efficient. That is, glass factories, steel mills, because the thermal radiation from ovens and kilns and steam furnaces, the railroad engines and so forth, that's waste heat. And so there was an international effort, countries worked independently to try to understand this waste heat to make them more influential in the industrial age. And people, using Herschel's techniques, built methods for measuring the visible part and the invisible part of the black body spectrum. So this gray bar represents the visible part, what humans can see. And over here we have ultraviolet, and here we have infrared. Here's an example of the infrared glow from different parts of the body. And a lot was discovered about descriptive laws were discovered. One of them is called the Wien displacement law. People noticed that if you plot the peak of the black body curve, you can see the peak is here and here and here and here. If you plot this in the right way, you end up seeing that there's a straight line that connects the peaks for black bodies of different temperatures. That was observational physics, no explanation until Max Planck. Once we have his formula, which looks like this, then suddenly everything was revealed by assuming that the light emitted by surfaces in kilns and furnaces and by the human body were all quantized. Then we get an explanation that this produces this simple equation, and with a little arithmetic you can show this must be the case, that if you plot the peaks on the right kind of graph paper, you get straight lines. Suddenly explanations abounded. In addition, people began to realize what was going on when they looked at the spectrum of the sun. So remember, I showed you a grating, and using a grating connected to an astronomical telescope, you get the spectrum of the sun. And if you have a big enough telescope and sensitive enough film, you can see the spectrum of galaxies and so forth. So people began to realize that any light source columnated by a slit and passed through a prism or a grating will produce a spectrum like this. This is a continuous spectrum. It's the result of a light source that's a heated body, for example, a furnace or a kiln or something like that. If we then look at spectra that looks like this, how do we explain this? It's the same light source surrounded by, in the case of the sun, surrounded by a cloud of gas that absorbs particular spectral lines. So that gas absorbs the lines, and we get these dark lines. For the sun, this was already known in the 1860s and 1870s, that the sun produced a continuous spectrum with some lines missing. And people also realized if you have a hot gas with no other thermal source, and you pass that through a prism, you see an emission spectrum. This is what happens in the case of the discharge tubes. So by some technique, you heat the gas, and the elevated energy levels of the electron produce this. So by the early 1900s, concepts or descriptive science existed. And in fact, it was in the public domain. Here's a stamp where Germany acknowledged Fraunhofer was the first to see the absorption lines in the solar spectrum. And this is a stamp in his honor. You can read this at your leisure. Still, the idea in the early 1900s of light being conveyed by photons, little puffs of energy, as opposed to waves, was still in doubt until 1923, when Compton did experiments that made it obvious that light is conveyed as photons. And Compton's experiment was based on using X-rays. X-rays X-ray photons are highly energetic photons. And his experiment is this simple, that he had a graphite target and single photons were coming out of that. You have the shield, and he was studying single crystals and was able to show effects that only could be associated with particles of energy, not waves. If you're interested in this topic, Feynman, famous American physicist, wrote an elegant little book. Here's the picture of the cover. You'll definitely enjoy reading this book, and it's very educational, and it's only probably 120 pages, but it's so explanatory. You've noticed I include little pieces of art as entertainment for all of us. Here's Niels Bohr. We'll learn much more about his description of hydrogen in just a few pages. This is his son, Aga Bohr. Both of them won Nobel Prizes. And this is the grandson, Thomas, who's a working physicist today. So what Bohr did in the early 19 teens was he developed a model of hydrogen that looks, it's in every textbook on quantum mechanics or modern physics. And it makes the hydrogen atom look like a little planetary system with the sun in the middle and an electron orbiting. And it has different orbits for different energy levels. Remember those N values I introduced a few pages earlier? This model is completely wrong. But Bohr, it still amazes me, Bohr's ability to use this model of a single electron orbiting at different energy levels, quantized energy levels, so that the energy and orbital properties of the electron were all dictated by this number, 1, 2, 3. There are, in Bohr's model, there are no values other than integers, 1, 2, 3, and so forth. This is, again, a version of quantization. Again, this model is wrong, but it produced a explosion of information because it explains hydrogen and other light elements that are ionized so that they have a single electron. You can use this model, I'll show you examples of it in a second. You can take lithium and ionize the lithium so that it only has one electron, and Bohr's model works. You can do the same thing for helium and beryllium and bismuth and so forth. Eventually you get to a point where this model doesn't work. But the idea is, sorry, went the wrong way, that those orbital properties in hydrogen dictate the energy levels that can occur. So if you energize the hydrogen in a discharge tube enough, you can get the electrons into these higher energy levels and you get transitions down to the lowest energy level. And when those transitions occur, you see these emission spectral lines. So the long ones are the Lyman series that produce ultraviolet radiation. Here's the Balmer series, which was the most accurately studied because it's visible radiation. And then you have the Paschen series in the infrared. So Bohr's model, even though it was wrong, explained all of this. And it furthermore explained something that had been observed in the 1880s, which was the Balmer formula. Balmer was, I think, a high school physics instructor. But in 1885, he had been looking at these kinds of spectral lines in hydrogen and produced this elegant little formula for characterizing the emissions of hydrogen. You just need two numbers. The two numbers we now know are the integers that describe this orbit for the electron in the Bohr model transitioning to this level. So from 6 to 5, or from 5 to 3. Some of these are not allowed. We'll talk about that in a future lecture. This is the so-called Balmer formula, and it was a revelation when this appeared in 1885. It's the only thing that Balmer did in his career. But Bohr knew about this, and he knew about quantization from Planck's model of the blackbody spectrum. And he knew about Einstein's work on showing that photons are individual quanta. They can behave as individual little puffs of energy. And he built his model, and in the process, he showed how to derive this number. It's called the Rydberg constant in the Balmer model. It sits right there, and if you know these two numbers and this number, you can calculate the wavelength of the transition, and they all matched this. So this is, other than Planck's, well, Balmer's formula in 1885 was the first equational description of what is seen in a discharge tube. And nobody knew why. And in the process, Balmer derived this number. That is, he figured it out from just putting integers in here and doing a little arithmetic. He got a number there that's called the Rydberg constant. Here it is. And it's based on other physical constants that were known at the time. This is what Bohr derived. He was able to explain the Rydberg constant, the mass of the electron, the charge of the electron, speed of light, a property of the vacuum of space, and this little parameter here, h. The key result from Planck's development of his formula for black body was not only did he explain the shapes of the black body curves and their sensitivity to temperature, he discovered that you had to define one number to scale everything properly to match it to the measurements, and that number is now called the Planck constant. So Planck not only found the formula, he figured out the numerical value needed in that one unknown parameter, now called the Planck constant, and that goes in here from Bohr's model of the Rydberg constant. And when I saw this the first time as an undergraduate physics major, well, you can see a little description here. I yelled to the professor from the back of the room where I was hiding, how does that work if Bohr's model of the atom is incorrect? And her answer was, we don't know. It's a miracle. But Bohr was able to explain the spectrum of hydrogen and a few other simple elements and derive the Rydberg constant. Later on, Arnold Sommerfeld made corrections related to Einstein's theory of relativity that made these predictions of spectral lines even more accurate. Whoops. Did a bad thing there. I'll have to fix this later, but you can see this little guy got out of place. And just keep in mind, Bohr's model was incorrect. These days, we understand Bohr's model, why it is defective, and we understand something that appeared in the 1920s from Paul Dirac. Bohr's example, here's an energy level in the Bohr model of hydrogen. Dirac studied this in detail in the 1920s and 30s and showed that if you do the right experiment, this line, this spectral line, which produces color, actually is split. There's actually two colors there if you look very closely, and it's an exquisitely detailed, complicated experiment to do this. It was done in the early 1950s, and sure enough, Dirac was right. That this line actually is two colors very close together. And now what would cause that? It has to do with the fact that the electron is buried in a cloud of virtual particles that are allowed by the uncertainty principle invented by Heisenberg. And those virtual particles are charged particles, and they shield the electron so that its charge is different than what you would measure if you had the electron isolated. So we get this splitting. And then later on in the early 1960s, late 50s, early 60s, more work was done, and it turns out this line, this color, is also split because of the spin properties of the electron. So progress continues. Now I'm going to stop for a minute and see if we have questions, and maybe the monitor who is protecting me from doing silly things can let me know if there are any questions.
We have 2 questions so far.
Okay, go ahead.
Okay, the first one is, when talking about gases, is the light source filled with those, or is the experiment enclosed in a gas-filled space?
Okay, so if we're using a discharge tube, the gas is in the tube, and then we run an electric current through the tube that energizes the gas, and the relaxation of electrons from higher energy states to lower produce the photons that we detect in the laboratory. I hope that's Now, the sun, different situation. The sun, the whole ball of gas that is the sun, is at temperatures that produce the same kind of effect. You don't have to run an electric current through it. And so we see the glowing ball of the sun producing emissions. And if you study the spectrum of the sun, you see all the chemical elements that are in the sun or in the coronosphere, the exterior sphere of gas around the sun. Okay, next question.
Okay, if all objects emit black body radiation distributed over a wavelength range that includes the visible, why does everything glow in the dark? Is this just a matter of how much radiation, or do cold objects not emit light in the visible spectrum?
Oh, excellent question. Let's go back to the picture of the black body curve. So it's the latter. Cold objects, like the glow from human skin, here's the black body spectrum for a 3000 Kelvin black body. Here's I'll show you later, the spectrum of the sun, 6000 Kelvin. Remember, this gray rectangle is the visual sensitivity of the human eye. When you get to 3000 kelvins, there's only a little bit of glow. If you go over here to, let's say, 300 Kelvin, which is the temperature here, remember, the human body is at around 20, 25 centigrade, but you have to add 273 to that to get Kelvin. A 300 Kelvin black body peaks way over here at 10 microns or 10,000 nanometers, and the human eye cannot see that. So everything is glowing, but you have to take into account the sensitivity of the human eye, which is only here. So if you're standing next to a embers from a fire, you see some glow. If you go out in the sunlight, you're seeing the white light emitted by the sun. Okay, we had two questions, is that right?
We just got another one.
Oh, okay, ask away.
Okay, if electrons have angular momentum but don't actually spin, how would you describe their motion? Is this one of those quantum mechanics unknowns?
It's a quantum mechanics unknown. And I think in chapter one, there's a footnote that explains that the classical physicists, remember the first generation of quantum physicists were all trained in classical physics. They knew about Newton and Maxwell's description of electromagnetism and so forth, and Faraday's experiments in the 1820s, I think. In those experiments, became obvious that moving current, electrical current moving through a wire produces a magnetic field. So when Uhlenbeck and Gauss-Schmidt proposed that electrons and other subatomic particles have magnetic properties, the assumption was there's electric current moving, and the electron, being a charged particle, is the source of that, generates its own magnetic field. It must be because the charge is moving. And right away, people went to the word spin because they imagined a little tiny ball spinning and producing its own magnetic field. That's not what's happening. There are particles in the subatomic family that have no charge, but they have a magnetic property. So we can set aside that idea that there's an electric current producing the magnetic field. Some of you may remember the movie Chinatown with Jack Nicholson. In the last line, Jack is confused. He's just suffered a terrible tragedy in Chinatown in Los Angeles, and his friend says, "Jake, it's Chinatown." Meaning that explains stuff that you just cannot explain. And to me, the magnetic properties of quantum particles is just quantum. We can't explain it. There it is. We understand it. We can describe it. That's true of a lot of physics. We can understand and describe exotic things, but description is not adequate. We want to know why. And at least I'm one who does not know why subatomic particles have magnetic properties. And it turns out those properties are critical to some of the things I've mentioned. For example, the construction of the periodic table of elements depends critically on understanding the magnetic properties of electrons. And we will get to that. So I've been talking for an hour. We are going to talk about the uncertainty principle next. So take a little break. And I'll see you in, let's say, 5 minutes, because I have a little demonstration I want to do. And so we have a lot to cover. So let's take a break. See you soon. Okay, folks, I am back. I'm just checking. Can you hear me?
Yes.
Yes.
Great. Well, your questions were great, but it reminds me, last week we had questions. I've re I put this little table in the folder where you see the various chapters. And I want to show something I did to help with this first question. An excellent question last week about how does the distance between the slits in a double slit experiment change what we see? So what I'm going to do now is I'm going to go back to chapter 1. Based on that question, I have modified chapter 1 and added an animated piece of software. So this is what it looks like. And I have to just for a second stop sharing because I'm going to show you my entire desktop. So you should still be seeing this graphic, but if you're interested in the question, the answer to the question that was posed last week, go back to chapter 1. There's a new version of chapter 1 and click on this little link. And you should see this. Now you get to decide the spacing of the slits, the width of the slit, and the number of slits. And if you want to see that, you just click on these little squares. Let me just ask, is that big enough to be seen, or do I need to make it bigger?
I would make it a little bigger if you can.
How about that?
That's perfect.
Great. Thank you.
So the way I built this, these two numbers are in units of the wavelengths of the light going through the double slit. So you just put in, if you want to use the same if you want the slits to be the same width as the wavelength, you just put a 1 there. If I change that to that value, it takes a second or two. Oh, and we only have 1 slit, so nothing changed. If I increment, this is what you would see, the blue curve. The orange curve is what happens if you only have 1 slit. So if I increase the spacing, you get more fringes. That's what these bright bars are. Now remember, this is a slice through the light that is recorded from the slit. If you increase the number of slits to 4, then you get narrow spikes. So I'll let you play with that. And once again, the way you get to that is you go to chapter 1. This is a new piece of art that you did not see last week. And here are questions and answers. These are in the folder. And I'll do the same this week. Okay. Now, is this page big enough, or does that need to be bigger?
I would do a little bigger if you can.
How about like that?
That's perfect.
All right, so here we're talking about the uncertainty principle that comes from Heisenberg, and it's a part of culture now to constantly, you can see this in the media, people referring to the uncertainty principle to explain various things that have nothing to do with the uncertainty principle. I would like you to read this because it explains that the knowledge we have about how waves behave comes from the period of around between 1800 and 1870 because of the work of scientists studying the double slit experiment, for example, and Maxwell's work to explain electromagnetism. The content of what was learned about how optical light, waves of light, behaves becomes critical in understanding how quantum mechanics works, because as we will learn, quantum mechanics is described by waves through a thing we call the wave function. And a direct connection exists between what we understand about how telescopes and magnifying glasses function and what their limitations are, leads directly to Heisenberg's uncertainty principle. So that's a good thing for you to read. And we will cover it many times. If you never get around to reading it, that's okay, because we are going to be constantly talking about the work of Louis de Broglie. De Broglie in the early 1920s had been highly influenced by Einstein's work to explain that light can be described as waves, and Einstein's efforts to show that light can be described as particles. It all depends on how you interact with them. De Broglie actually he and his brother, who were rich children of an industrialist, had a laboratory in their estate in France, and they did experiments. And when de Broglie went to do his PhD, he proposed that if light can be particles or waves, then physical quanta, like electrons and protons, by then protons were around, physical items like protons, electrons, neutrons, all that, that they could be described by having particle or wave-like properties. And this was a revolutionary idea. De Broglie had to fight to win his PhD because there was so much controversy about his idea. Fortunately, he had Einstein on his side. And Einstein said, I believe it is the first feeble ray of light on this worst of our physics enigmas. De Broglie got his PhD 1927. It's on the page here somewhere. Just a few years later, Davison and Germer won the Nobel Prize for demonstrating that electrons behave like waves when you use them to illuminate crystals of the metal nickel. If you prepare nickel properly, it has the atomic array in the metal is a very regular structure that we call a crystal, equally spaced atoms bound together by the electrons that they share. Davison and his colleague Germer were able to demonstrate that illuminating nickel with X-ray light produced undeniably wave-like results. Results like I just showed you in that little model that I built to answer the question. Let's just go quickly look at that. In the case of shining X-rays on nickel, you have lots of atoms interacting with the waves of the electrons. So you get lots of these spikes. And Davison and Germer did their experiment, and at the same time, George Thomson did a similar thing. Both won shares of the Nobel Prize, and along with de Broglie, for demonstrating wave-like properties of particles, quantum particles behaving like waves. The interesting thing comes from this sentence. 30 years later, Thomson's father, 30 years earlier, had demonstrated that electrons are particles in his experiments, and he won a Nobel Prize. And then this Thomson won for proving that electrons are waves. And poor Mary here because of the Heisenberg uncertainty principle. She can't find her keys because she knows where she is, or she can't find her keys because she knows where he is. If you read the caption, you'll see there's a sad little joke there. Okay. De Broglie's effort was a major step forward in understanding quantum mechanics because he predicted wave-like features of matter, and the experiments that occurred just years later showed that he was right. This advance in 1922 through 26 had a tremendous impact on Erwin Schrödinger, who in late 1926 introduced for the first time an equation that describes the behavior of the wave interpretation of quantum mechanics. I mentioned a term a few minutes ago, wave function. Schrödinger wrote the first equation that describes the evolution of the wave function. In addition, he was impacted by de Broglie's effort. There's a quote here about it. In addition, de Broglie opened up the possibility of reinterpreting Niels Bohr's model of the hydrogen atom. The idea being, if you have a wave going around the orbit of an electron orbiting the nucleus of a hydrogen atom, it must be described as full waves. Here's a cartoon that shows what you might expect if you look at the strings of a guitar or a harp or something like that. Waves propagate in the string, but the two ends are fixed. That is, the two ends must have the same value. Otherwise, you'd have a gap in your string that goes around the orbit. So thinking about Bohr's model of hydrogen, which came out in 1913, 10 years later, de Broglie said if electrons can behave like particles or waves, when they are in the wave state, they have to be described by integer values. So here we have a single arc. Here we have two arcs. We have three, but values that don't have integer description are not allowed. And that was the assumption that Bohr had made in 1913 when he described his planetary model for hydrogen and other atoms. So de Broglie, and I mentioned he and his brother, de Broglie, his brother Maurice, doing X-ray experiments in the basement of their estate in France, did very fine work. And in fact, de Broglie won the Nobel Prize. They were also nominated for the Nobel Prize because of their research in X-rays. So what comes out of all of this is the wave-like properties of particles and waves. That is, particles could behave like waves and vice versa, depending on the environment in which they find themselves. And we'll hear much more about this wave-like property later, but what's really critical is to understand the reconsideration of Bohr's model, the properties of the electron shifted from looking like little particles like BBs to waves described by Schrödinger's equation. That happened in 1926, and the result was a new interpretation of quantum mechanics that has not changed substantially since that time 100 years ago. The fact that we all have cell phones and all kinds of advanced electronic technology and all the benefits that come from that knowledge appeared in 1926. And it's the Schrödinger equation that dictates how the subatomic world behaves. We will see much more on this. Now, we also have to include this issue about spin. I've already explained that the term spin is a bit misleading. Nothing is spinning, but all of the subatomic particles have magnetic properties and associated angular momentum. You might remember if you in a physics class in high school or college where someone was asked to sit on a piano stool and the teacher handed them a bicycle wheel that was spun up to a high speed. And the idea was the student was try to tilt the wheel. If you've done the experiment yourself, you know it's very difficult to tilt a highly spinning wheel. That's why it's relatively safe to ride a bicycle, because the angular momentum of the wheels stabilizes the machine. Uhlenbeck and Goldschmidt were graduate students. They were looking at spectra. This is 1922, 23. Uhlenbeck and Goldschmidt were looking at spectra, and they began to realize there's something about the splitting of the spectrum in the Stark effect. Remember, that's the one where you impose a magnetic field on the light, the gas in a discharge tube. It occurred to them, maybe there's another quantum other than the energy quantum. Remember, I introduced that with the letter N for the amount of energy the electron has. They thought maybe there's another quantum number that somehow relates to magnets. Maybe the electrons in atoms have properties, have magnetic properties. It turns out they did not know this, but earlier, both Kronig, I think he's an American, and Compton, also an American, had suggested at meetings, I mean, they didn't write papers on this, but they talked to people about, I wonder if electrons have magnetic properties, and both were convinced that they would not help their career to talk about something that irrational. Nonetheless, Uhlenbeck and Goldschmidt were too young to know not to bring this up. So they went to their professor and they said, we think electrons have magnetic properties. And he said, it sounds not right, but why don't you write it up and I'll read what you have written. So they wrote it up and they gave it to their professor, Ehrenfest. Ehrenfest was well-connected, a highly influential person, and he contacted Niels Bohr. So Ehrenfest, Uhlenbeck, Goldschmidt were in Leiden, a couple hundred miles from Copenhagen. So he contacted Bohr, and he said, my students have this idea of spin, and there's a discussion here of what spin is about. I will end up talking about this endlessly, so if you don't read this, that's okay. So anyway, Bohr got involved and he said, now that's a very interesting idea, which contemporaries of Bohr said that's the way he conveyed the idea that it was a stupid idea. He would say, that's very interesting. Nonetheless, Bohr started thinking about this. I'm going to something. And it turned out he was headed to a conference in Berlin. So Bohr is on the train thinking, and he got to Hamburg, where two giants of quantum mechanics, Wolfgang Pauli and Oscar Stern, had heard about the idea of spin, and they were waiting for the train with Bohr on it. And they got on the train and ran up and down the aisle until they found Bohr and said, what do you think of this spin idea? And he said, it can't be right. It makes no sense. So he got back on the train. And of course, as soon as he did that, people started writing letters to each other saying Bohr doesn't believe in spin. So Bohr goes to Leiden, which is near Amsterdam. Ehrenfest and Einstein were there. They meet Bohr on the train or the train platform, and they said, what do you think of spin? And he said, well, there's a problem. It has to do with relativity. And Einstein said, I already solved that problem, and explained what he had done. And Bohr was convinced, hey, spin is a good thing. Gets back on the train. You see how this is going. He goes to Göttingen, meets Heisenberg and Jordan. Now Bohr is passionate about the idea of spin. It explains a lot. Goes to this meeting in Hamburg. So in his tour around Northern Europe, his mind changed 3 or 4 times. But eventually, the whole community got on board with the idea that there are magnetic properties of electrons. And let me explain the bizarro property. You can go to your refrigerator right now. You probably have magnets on your refrigerator. And we all know from experimenting and being told so in elementary school that there's a north and south pole of a magnet. You can't put the two norths together and you can't put the two souths together. And it all sorts of makes sense. It makes sense. Here's the bizarro property of the electron. Its spin in some convenient units is 1/2. No matter how you measure it, it only has 2 outcomes from an experiment of measuring the spin of the electron. It's either positive or negative. There are no in-betweens when it comes to the spin of charged subatomic particles. And I will usually talk about electrons when I'm describing these things. So every experiment that is done, sorry, I see an error here. I'm going to just light that up a little bit and edit it. Well, never mind. I'll fix it later. Any measurement of the spin of subatomic particles or atoms produces an integer number of results. Why do I say integer? Because between positive 1/2 and negative 1/2, and subtract one from the other, you get the number 1. A complex atom, I'll show you one later, has a spin of something like 5 or 7 or 8 because of the orientation of the electrons. But the spin is always quantized. And by quantized, I mean the difference between different values has to be 1 or 1/2. It can't be 0.73 or something. So again, we have quantization. Remember, I talked about the energy levels of hydrogen and other atoms, usually abbreviated by the letter N. N has to be integer. The spin in quantum particles has to be integer. And so we continue to find evidence for, sorry, I gotta do something. We continue to find evidence for quantization, including in the black body spectrum discovered by Planck in 1900. So we've now covered some of the more technical details that occurred between 1900 and 1927. And the old quantum mechanics that was invented by Bohr, the planetary model, was set aside because it turned out Schrodinger's wave function model produced the same results without the very misleading idea that electrons are little ball bearings and so forth. We'll get into that more. Here's a description. I already showed you the picture. Here's a description of Davison and Germer's experiment influenced by de Broglie's thesis. These two guys were industrial physicists whose job was to study the mechanical properties of alloys, metal alloys. And it turns out they had just the right stuff to do an experiment that could confirm or deny de Broglie's PhD suggestion that photons can behave like particles or wave, and electrons can behave as particles or waves. And all they needed to do with their experiment was replace the alloy they were experimenting with a crystalline solid, namely crystalline nickel. So you had to learn how to make crystalline nickel. Normal nickel that comes out of a foundry has a random array of atoms. Properly created, you can make crystalline things. Crystalline solid of nickel, for example. And here's what they got when they illuminated their single crystal nickel with X-rays. These bumps, just like this, indicate wave-like behavior. Now, I haven't emphasized that enough. The double slit experiment that we've talked about a few times and we'll keep talking about only can produce this kind of characteristic spaced spikes if you're passing waves through a double slit experiment. In this case, I've got 6 slits, and you see lots of spiking and so forth. That's the same thing Davison and Germer got from illuminating their nickel crystal, which is illustrated here, with a spacing between the atoms of 352 trillionths of a meter. Crystalline nickel. So this was a compelling piece of evidence for the correctness of de Broglie's idea that the X-rays that they were working with actually were behaving like waves and were scattering and producing wave-like results. Another piece of evidence for particle-like behavior was the cloud chamber, which was invented in 1911 or something. This is a track of the first negative electrons, called a positron. First positron ever detected was detected in a cloud chamber. So the idea of the cloud chamber is not unlike the conditions that you see when an airplane flies over and a vapor trail appears behind the airplane. That is low pressure, and in clean air environments, water vapor does not condense unless there are some kind of they're called nucleation sites, little pieces of dust or something that cause the supercooled water vapor to condense. The atmosphere just remains clear. But if an airplane flies through and the exhaust has all kinds of little unburnt pieces of fuel and so forth, the water vapor condenses and we see a vapor trail. And the invention of the cloud chamber made it possible for many things to happen. First of all, Wilson, the inventor, who won the Nobel Prize in 1927, he could see tracks of charged particles moving in Earth's magnetic field or experimental magnetic fields as curved tracks indicating charged particles. And he could see cosmic rays, the shower of debris caused by cosmic rays hitting the upper Earth atmosphere and producing a shower of subatomic particles. So this is a great experimental advance. This also demonstrated that particles could produce this kind of vapor trail, a wave-like particle, or a particle passing through would cause that kind of condensation. So what we have is an accumulating list of pieces of evidence from the double slit experiment. Here's a quote from a recent book on this. The double slit experiment brings out the wave properties of the photon or electron. And we will be considering this more. At this point, I want to do a demonstration for you. I'm going to stop sharing my screen. And you should be able to see me. Hello, everybody. Now, what I have here, oh, and you should be able to see the background. There are windows and a clock and so forth. What I'm going to show you is something, I'm going to plant a seed for something we are going to be doing in the future about how particles of light, namely photons, behave. And to do it, I'm going to use a polarizing sheet. So you see it's kind of has a gray tint to it. These are plastic sheets that have a polymer embedded in them that behaves like your sunglasses do. You know, if you put one of these up and rotate it, it does have an effect of rejecting scattered light. So right now, there's not much scattering. If I rotate it, you see those streaks? That's light in the room reflecting off of various surfaces. Now, you've all done this experiment with, or could have, with sunglasses. I've now got two sheets, one in front of the other, and they're, if I orient them this way, you can see through. If I cross the orientation, you see this region right here is no light coming, or essentially no light coming through. So keep in mind, we're doing an experiment on waves of light. Normally, when we are observing the world around us with our eyes or cameras, we're able to accurately describe what's happening, treating light as waves. In reality, light behaves like particles too. And here's the intriguing thing that happens. I have a third polarizer. There it is. Watch what happens when. Now remember, there's essentially no transmission. I'll put that up. It's very little light coming through. We put this one in at an angle. And can you see that this third one that's in between the other two restores the transmission of the two that were opaque? This is a surprising result. And I want you to consider, how are we going to describe this when we reconsider this experiment, treating light as particles, individual photons? So this is an experiment. You can do it with go to the thrift store and buy 2 pair of polarized sunglasses and break them so that you can take out the lenses, and you can do this experiment at home and challenge your grandchild to try to explain why adding a polarizer improves the transmission from 0 to something not 0. Okay, let's get back to what we were doing. I'm going to go back to the desktop. How much time? Okay, let me stop at this point and see if we have questions.
Yes, we got 3 questions.
Okay, great.
In the interactive slit graphic, it doesn't look like the integral under the various curves is constant for the different parameter sets. Should I not be expecting that the total light is a constant, or is this an artifact of the way the plot is set up?
Okay, so what the question pertains to, this is a person who has studied calculus. The integral, what they're talking about is where'd the energy go? So let's go back to one slit. This is, if you add these little bumps here and this big bump here, you add up all the energy that came to the double slit. So if you add this up, and let's call that 100%. Now, if I change, let me change some values here. We're going to go to 2 slits. If you add this up, it doesn't look like it, but in fact, the area under the blue curve is the same as the area under this orange curve, because energy is over here outside the bounds I chose to do for the plot. There are a large number of bumps over here and over here that I didn't, I just stopped plotting right there. But the amount of energy in the experiment has not changed. Okay, let's go to the next question.
Does an electron by itself have a spin property, or is it only observed by having the electron interact with other particles and or magnetic fields? Does spin exist if you don't measure it?
This is a fantastic question. Uh, if you talk to Niels Bohr, if you could resurrect Niels Bohr and ask him, does an electron have a spin if you don't measure it? He would say, don't ask me that question. There's no way to know anything about a quantum system unless you make a measurement. Now, that ends the quote from Niels Bohr. If you ask the modern physicist the same question, does the spin exist if I don't measure it? That modern physicist would say, I'm not going to talk to you about that. I don't know. I don't know of a way of knowing. And the question is so on point with the focus of this class because there are many interpretations of quantum mechanics. You will see a bunch of them in lecture 6. They all have different views of the answer to that question. Is there an I'll recast the question. Is there an existing reality that is independent of observers, that exists in the universe, whether we are looking or not? And if you ask 6 different physicists, you will get 5 of them saying, I don't have time for that question. I'm going back to the lab and create the next generation of fantastic products. The number of physicists who worry about this kind of question is exceedingly small, but it's a topic which is growing in significance because of quantum computing. Because understanding what the quantum world is doing is now on and in the thinking of any physicist who's dealing with quantum computing or knows about it or knows about quantum cryptology wants to know more about the reality of the quantum world. But the question is unanswerable. So again, Niels Bohr built his research center in Copenhagen, and that whole school and all the students who went there and were influenced by him, and he was a giant in quantum mechanics his whole life. That is called the Copenhagen School, and their idea is nothing is known about quantum systems until you measure them. And we are going to, next week, we will begin dipping our toe gradually more and more into the bizarre experiments that have been developed to demonstrate that in some sense Bohr was right, but in another sense, it seems like his philosophy for what's happening in the quantum world is dominated by avoiding questions like this one. So I congratulate whoever asked that question. It was just a profound and deep question. All right, let's go to the next question.
Okay. Does the scattering of electrons by single crystal nickel change with temperature? Are the wavelengths of the peaks a result of interaction with the nuclei, or are they that are separated precisely, or is it a result of interacting with the electrons in the lattice?
Yeah, so there is a small effect from temperature. I have not done this experiment. And by the way, this is an actual result back from the 1920s. I think if you heat up the nickel, these lines, these peaks spread out, indicating that motion within the crystal, between the atoms in the crystal, will blur out this effect. The interaction is going on between the photons projected into, okay, wait a second. I'm going to defer answering the business about, is it the electrons that are causing the diffraction, or is it the nuclei? Because remember, in a crystal, the electrons all are shared by all the nuclei, so you can't associate uh, the electrons with a specific nucleus. That's a good question. I'm gonna give that some thought. Okay, is that the last of the questions?
Yes, that's all I have.
Okay, I particularly like the last question. That's very interesting. Here's the demo I just did. Let's take another look. I do have photographs of the Polaroid demonstration that I just showed you, where I have a single sheet. You can see my camera took a picture of my computer screen. Then I had two sheets crossed. You can't see anything. And then I put a third one in between, and suddenly transmission is restored. We're going to be talking about that. Here's a drawing of the same thing, the polarizing property of the first sheet, the last sheet, and when it's crossed like this, no light gets through. But when we put one in at an angle, we get transmission. And now we have about 15 minutes left. I need to look ahead. Yes, excellent. So keeping that polarizer experiment in mind, let's take a look at a tremendously influential experiment that dates to 1922, Stern and Gerlach. And here's a drawing you can get from Wikipedia. What's going on here? Instead of using photons on a double slit experiment, Stern and Gerlach had the equipment necessary to test Bohr's model of atoms, that electrons are in orbits. Remember, 1922, the idea of spin was not in the atmosphere yet. It was still waiting for Bohr to make a decision about whether it was real or not. Nonetheless, Stern and Gerlach came up with a brilliant experiment to measure the magnetic properties of atoms. Here's what they did. They had an oven, and they put silver in the oven, so that a beam of silver atoms came out. And we have a couple of collimators to make the beam clean and neat. And then they invented this brilliant interpretation of a magnet poles. So they have a north pole. These are magnets. The north pole has a sharp point here, and the south pole is like a trough, and the beam goes through here. Now, if we were doing this experiment, we'd say if there are magnetic properties of the atoms, and the atoms come out of the oven in all different orientations, we should expect to see a smear of atoms collect on a target. So they had a metal plate here, and they would do this like for a couple hours and then inspect the plate and see where the atoms are. But you don't get this. You don't get a smear. You get two results. This is just like the thing I told you about electrons. If you run electrons through a magnetic experiment, you only get one of two results. Either the electron points up or it points down. And that's what Stern and Gerlach got for silver atoms, even though there's nothing here to make the atoms orient. They got as many ups as downs. So they didn't get this. And this had a tremendous impact on how people thought about the magnetic properties of atoms. And what they realized was silver has an odd number of electrons. And if you look in detail at how those electrons are packed into the various electron orbits, to use Bohr's terminology, the electrons are in different orbits or shells. That's the modern chemistry description. You have an electron, a leftover, number 47, And it turns out that that electron dictates how the atoms individually interact with this magnetic field. And you get two results. So almost identically at the same time that Uhlenbeck and Gauss-Schmidt were proposing that electrons have spin or magnetic properties, Stern and Gerlach were doing the experiment that proved it so. So you only get two results. And it's intriguing to look at how there's stuff to read here. We don't have time to cover it all, of course. Here's a postcard that Stern and Gerlach sent to Niels Bohr. You can see there, he's addressed to Niels Bohr. And they said, "Dear Professor, we did our experiment and we turned off the magnets." Remember, these are electromagnets, so you can turn them off or on. We turn them off, we just get this result. But when we turn the magnet on, in the place where the magnetic field is the most intense, we get a separation. We either get, in this case, up is this way, down is over here. We get a separation in the most intense area of the magnetic field. We get what is now called the smile. You can see why they called it that. And this, along with information or conjecture by Uhlenbeck and Gauss-Schmidt, made people think very seriously about the influence of the electrons in the outer shells of large complex atoms such as silver with 47 electrons. Things started coming together. By the way, here's Stern doing experiments. The interesting thing is when they did their experiment in a vacuum, and then they had to open it up to look at the target to see where the various atoms hit the target. And what they discovered was they didn't see anything. So they went and had lunch or something. When they came back, suddenly they saw the impact points of the various atoms. And it turns out it came from this cigar. Stern was famous for constantly smoking cigars in the lab. And the smoke from the cigar includes sulfur. And the silver atoms, once they got in contact with the smoke in the lab, produced silver sulfide, which has a black or gray look to it. And they could see the results. Had he not been a smoker, they would not have had results. Here's what's really intriguing. Here's the source. Now, everything's turned around because I chose this piece of art from Wikipedia. Here's the source of atoms. Here's the magnet. And you get either ups or downs, nothing in between, which indicates there's some kind of quantization of the spin of that electron, that 47th electron. Now, to clarify, we're going to do an extended experiment. We're going to block this beam. And now I just have to tell you, Z is the dimension upward in this drawing. So you get either Z up or Z down, meaning either the beam was deflected upward or downward, compared with a vertical line here. So we block the Z beam, and now we're going to build another Stern-Gerlach device and rotate it by 90 degrees. In the case of polarization, if this were a polarization experiment and you shine a light on the first polarizer and then one that's at 90 degrees, you get nothing over here, right? We did that in the experiment a few minutes ago. But in the case of the Stern-Gerlach experiment, the beam, we save half the beam, and it encounters an identical piece of hardware rotated at 90 degrees, and you get two spots again. What this tells us is there's something about the relationship of the orientation of this magnet and this one such that this beam right here, this is all atoms oriented upward in the laboratory, that gets lost. The technical term that is used, it gets scrambled if you put the beam this way. And why does that happen? Why do we get 2 new spots. And the answer is the uncertainty principle tells us you cannot measure this dimension and this dimension at the same time. Let's keep going. So Stern-Gerlach is just tremendously influential. And let's reflect back on the question that was asked a few minutes ago about electrons. What do we know about the spin of an electron if we don't measure it? This is a piece of artwork I drew. If we have a source of atoms and we shine them into a Stern-Gerlach experiment, we have no idea what's going on in here because there's no measurement being made in here. We have no idea what's happening between the exit of the magnet and the screen, except that we will discover we get 2 spots. There's no way to know what's happening in this interim. And in fact, professional physicists don't understand this at all. Let me convince you of this. You see these little cartoons I've drawn? They come from a dozen or so physics books. Each of the books talks about Stern-Gerlach experiment. There's the oven, the side view of the magnets. And in Yauk's book, I've copied the trajectory that he has included in his book. He thinks the beam of atoms comes out and then they split. Hurdle, also a respected author, he says the split starts right at the beginning of the magnets. Townsend says, yeah, it starts at the beginning, but the trajectories are straight lines. If you look closely, you'll find every one of these drawings is different. Professional physicists do not know what's happening inside this experiment or getting to the screen. This is the screen. All we know is we have a beam of atoms and we get 2 spots. So that's, once again, reflect back on that question I was asked about, do we know anything about the spin of electrons if we don't measure them? The answer is no, we know nothing. Here's Stern and Gerlach being shown. There's the smile that I mentioned. This is on the side of a building in Frankfurt where they did their experiments. Let's see, we have just 2 minutes left. Maybe we should stop here and ask, are there any questions?
I do not have any new questions.
Okay, good, because I want to make sure we cover this today. I mentioned earlier, the electron has spin 1/2. So it can only be up and down or down. Here we see cesium, a particular isotope of cesium has spin 4. The spin comes partially from the electrons in the atom, not only their orientation, but their motion. And I'm using language that's a bit misleading because if you talk about motion of an electron, it makes it sound like an electron is like a bowling ball. It's not. It's part of a cloud of probability of where you might find an electron if you were able to do the experiment. And we're not. You can't dive into an atom and see the electrons. But we can do experiments with spin, and here's cesium-133. It has spin 4, partly from the orientation of its electrons and partly from the orbital behavior of the electrons. And remember I said that electrons, or all the differences, have to be equal to unity. So from 1/2 to 1, from 1/2 to -1/2 is 1. From 0 to 1, 2, 3, 4, those are the only allowed orientations. But if I have the number 4, how many different units can exist? If I start at -4, I have -4, -3, -2. They're all illustrated here. -4, 3, 2, 1, 0, 1, 2, and 3, and 4. There's 9 different orientations possible for the spin of cesium-133. And this is data from an experiment that demonstrates that. There's a tiny little bump there and one there, and then it becomes very obvious where the bumps are. this is a spin measurement for cesium-133, indicating that the increment in spin has to be integer values and there's nothing in between. The fact that there's something there is just the limitation of this experiment. So let me close by saying there's more information on these results, including this panel that discusses the spin orientation and some more advanced ideas we might reflect on in later lectures. But I will just close by putting up this piece of art and letting you ponder it. If we have a source and we stop the Z minus atoms, and then we pass the Z plus atoms, we get two outputs. We get a Z minus and a Z plus. And if we run that in through another one that's reoriented, notice this one's up, down, this is sideways, this one's up, down, then we get two spots again. So we're beginning to see some of the bizarro behavior of the quantum world. Thank you for sticking with me. I know this is hard to digest, but we're going to keep talking about it until we all understand it. And here's a sculpture in Moscow you might want to visit someday, maybe not, of Einstein and Niels Bohr. So thank you to the people at CSU Fort Collins for taking notes. I'm going to answer questions. So you can submit questions to the university, to the Osher Center, and they'll pass them on to me. And I'll see you next week for lecture 3.
Thank you.
Hey, good day.